Well, I mean, there is the question of the collapse of the wave function, which I think maybe a lot of people thought was philosophy. I don't know. I take the view that it's genuine physics which you don't yet understand. Not that we just don't understand. Not understanding rather implies that the theory is out there which we haven't grasped. And I think often people take quantum mechanics in that sense. They say it's a mysterious subject, and it takes you're not going to be able to understand it properly without really realizing there's that deep mystery in it. That's not the way I like to look at it. I tend to look at the problems in quantum mechanics are really that we don't fully have the theory, that the collapse of the wave function is a physical process which needs to be understood properly, and there are experiments which probe the nature of that area. So I'm trying to bring that thing more into the realm of physics rather than as it might have been sort of hovering around as a philosophical issue.
So let's talk about this topic of consciousness. As you mentioned, traditionally it was thought to be a purely philosophical topic rather than a scientific one. But from the early days of quantum mechanics, there was this interpretation that consciousness had something to do with the collapse of the wave function, that somehow consciousness measurement involving a conscious observer was the thing that made the wave function collapse from a state of superposition.
Yes.
But you're not very convinced by that interpretation.
Well, you see, I have almost the opposite view. I think the terminology drove people in that way. It's like saying you make an observation. And when you made an observation, you had to change the rules. Up to that point, you take the Schrödinger equation as describing the evolution of the physical world. And then when an observation is made, it's only telling you the result of an observation. But then the observation was really something outside physics. Whereas the view I would take is that we should be looking for a physical theory which reduces the state. We don't have the physical theory yet, although I think, in my view, it's going to be something to do with how gravity relates to quantum mechanics. And that when a system becomes big enough for its gravitational fields to become significant, then you have to bring it into account. And the measurement process, it's not really a measurement process, it's a collapse of the wave function process, which is actually something which happens. It's independent of how you only measure something because you tie the system you're observing into a bigger system, which is making the measurement. And so you're really looking at how that physical system behaves as a whole. And of course, on mathematical logic by a man called Steen, and his lectures made clear to me, at least what seemed to be clear to me, that conscious understanding could not be an algorithmic process. There's something different from computational processes going on. So if we believe that whatever we are, we're sort of physical structures, then do we act according to computational laws, or is there something in the laws of physics which is outside that? And the view I maintained at that time, because of the lectures, Steen's lectures on mathematical logic and Gödel's theorem, it seemed clear to me that conscious understanding had to be something which was not computational. And then the question is, if it is a physical process of some sort, what could that physics be? And if I think about classical Newtonian mechanics, it didn't seem to be much chance. Even general relativity, because you could put these things on computers. There is a bit of an issue about the fact that theories depend on continuous parameters, whereas computation, as normally understood, is a discrete process. And the way we do calculations in physics to mirror what's going on in the world and put them on computers, we regard these as approximations which you could refine as much as you like. And they're still then computational processes. There's a little bit of a problem there about whether there might be a distinct difference in continuous evolution from discrete processes. But I didn't think that was the answer. It seemed to me that there had to be physical processes which were not computational. And the view is that this is conscious understanding has to be one of these. And where in physics do we see anything not computational, or anything of relevance that would be not computational? And it seemed to me it had to be the collapse of the wave function.
Why is the physics of quantum mechanics and the collapse of the wave function specifically non-computational compared to the rest of the physics?
Well, the argument's really the other way around. It's not saying why that's non-computational. It's the argument was, if we need something non-computational, what could it be? The argument's that way around. And if it's just classical processes, even general relativity, even if it's quantum with regard to following the Schrödinger equation, I see nothing non-computational in that, because there's things you could put on a computer. So if there is something non-computational, it's got to be outside any of those views. And what has a chance of being outside? Well, collapse of the wave function. So it's more a process of elimination rather than expecting to see it there.
So that was your reasoning for thinking there was a connection between consciousness and the collapse of the wave function.
Yes.
Now to the understanding of how to think of that. How do you think of this phenomenon? How do you see consciousness arising?
The collapse of the wave function, how do I see it? Well, I think that required a lot of refinement as time went on. And in fact, when I wrote The Emperor's New Mind, although I had the view, that general view, I didn't have what I now believe to be the right criterion. Although I did think it was gravitational. What I regard as being the right criterion, or at least towards being the right criterion, is dependent on an argument which I can't remember exactly when I first thought of this argument, but it's showing an incompatibility between the principle of equivalence, the equivalence between a uniform gravitational field and an acceleration. So it's the Galileo principle, if you like. Imagine a big rock and a little rock dropped from the Leaning Tower of Pisa, and they drop together, as Galileo was clearly pointing out. And that principle is the basis of general relativity, combined with special relativity, if you like. You've got speed of light being fitted in with being a constant of nature, and time and space being part of one structure of space-time. And then Einstein modifies that picture by introducing the principle of equivalence and saying that gravity is not a force. It's you can get rid of it by falling freely with it. However, if the force is not uniform, or the gravitational acceleration field is not uniform, you're led into a curved space-time. Now, the argument that I was making was that if you have a principle of equivalence, there are two ways of looking at a quantum system in which you want to take the Earth's gravitational field into consideration. The way that any sensible physicist would use, and when I say sensible, I mean just the normal way, would be to do what's called putting a term in the Hamiltonian. You have your standard quantum mechanical procedure, and you accommodate the Earth's gravitational field by putting this extra term in the Hamiltonian. That's the Newtonian way of doing it, if you like. You're thinking of gravitational force, it's just another force. Then you say, what's the Einsteinian way of looking at it? Well, you say, take the principle of equivalence seriously, and falling free, if you have a uniform gravitational field, you can consider describing that system with a coordinate system which is dropping freely. And then there is no gravitational field. It's just using an accelerating frame. And then you compare the two procedures. And what you find is that they're almost exactly the same, but the key is in the almost. The difference is in what's called a phase factor. And the usual attitude in quantum mechanics is to ignore the phase factor. You say these two states are the same. So you could ignore it. That's not quite fair, because you look carefully at the nature of this phase factor, and you see it involves a term where the time comes in cubed. The gist of all this is that you are doing a different quantum field theory. You have to know what the quantum vacuum is in order to do your quantum field theory properly. And the vacuum is different if you take the Newtonian perspective and the Einsteinian perspective. Again, you might say, who cares? Stick to your vacuum and you get a consistent answer. So why bother? This is all right as long as your field is a constant field, like the Earth's gravitational field. It's a bit like going back to Galileo and say, you can get rid of gravity if you fall freely in it. But it doesn't quite work if, as you move around, the field is in a different direction. So it's all right to say you can get rid of this field vertically downwards here, but what about in Tasmania or something? You see, it's a different direction. So to hang together your theory where these directions are moving as you move around is a challenge. And what it leads you to is an inconsistency. You can't really quite do it. And so what you have to do is try and estimate the error involved in this. And that estimate gives you have to do a little bit of mathematics. And you see that that comes to a sort of uncertainty in the energy of the system. And that uncertainty in the energy in the system you can interpret as a lifetime of the system. This is going to Heisenberg, and you have this Heisenberg time energy uncertainty. So if you have an energy uncertainty, that is related to a lifetime. You get this for particle physics. For an unstable nucleus, there is an energy uncertainty which is inversely related to its lifetime. So the argument then is your quantum superposition, which has this tension in it, which is an energy uncertainty. You can work out the lifetime. So that lifetime tells you how long a quantum superposition will last. It turns out that this actual formula I had was found already by Dioschi, another physicist who some years before me had put that forward. So it's sometimes called the Dioschi-Penrose model. The rest of the theory is not quite the same. He has a different way of looking at things from me. So they are different theories, really. But the lifetime is the same criteria as he had. Now, in when I wrote The Emperor's New Mind, I didn't have that quite right. And having it, when I say quite right, I didn't have the current view I have on this. Whereas in Shadows of the Mind, which is the next book I wrote, I put in what I now believe to be the correct criterion. There are some subtleties about it which I hadn't realized at that time. And these lead us into interesting territory.